So the next exciting thing that we're going to talk about is amino acids. And amino acids, as you probably are familiar with already, make up the basic building blocks of proteins in the body. So we're talking about 20 of those that are the major ones. You can look that up on many different websites and figure out which ones you have there. Let's talk about why it is that this is called an amino acid. Well, on one side of the structure, we have an amine. And that amine is simply right here. We've got an N right there. And on the other side of the structure, we have, you guessed it, a carboxylic acid. And therefore, we have something that is on one side a base and on the other an acid. And so we're going to talk about in just a minute how pH can affect what these look like. But for the most of the time, these will look simply like you see over here in this box, okay? Well, I should say that the basic structure looks like this. You then have some type of R group up top. So we have a centralized carbon in the middle. So he's right here. And we tend to write this so that on the left we have N, but it really at physiological pH most of the time is NH3 with a positive charge on that nitrogen. Because, remember, we said that the amine was a base. And on the right-hand side, we have a COO minus. Now, why is that going to be negative? Remember, we said that the carboxylic acid was an acid. So it gives away its positive or its hydrogen, and nitrogen accepts a proton or a positive hydrogen, right? So this is actually what we refer to in science or in chemistry as a Zwitter ion, and that's not something that's seen very often, but amino acids definitely have them up there. So attached to that central carbon right there, we have some form of R group. But y'all, that first thing that I boxed in here, this stuff, that's sort of the same no matter what type of amino acid you're looking at, which means that the R group is defining which amino acid you actually have. So remember how we talked about like your body prefers one enantiomer over the other? Well, we only have L enantiomers of amino acids or in proteins. So we call NH3 is on the left, and that's the reason why we write it. So the NH3 is on the left, and our carboxylate is on the right. So we call that a carboxylate instead of a carboxylic acid just because it's missing its acid portion, so the H is gone. Okay, so the reason why the COOH is COO minus and NH2 is sort of just, explained a little bit further down here, and we'll talk about that on the next page as well. So this says positive and negative, just so you know. But if a positive and a negative exist in the same molecule, that's what I mean by a Zwitter ion. That's the funnest word in the world to say, is Zwitter ion. It actually is a Zwitter, and then it has the term ion there because you have both positive and negative there in the same guy. It means that there's a total charge of 0 for each amino acid. The point at which the amino acid has a 0 charge is something we refer to as the isoelectric point, okay? Now, there are different classes of amino acids. And those different classes are defined by what their R groups look like because otherwise everything looks the same. So we have things that are nonpolar. Those are R groups that have basically, we've got carbon and hydrogen bonds there. Things that are polar, so things that tend to have oxygen or can hydrogen bond in those R groups. And then we have those that are charged at physiological pH, which is about 7.4. And you can see several different types of amino acid classifications that have those three groupings to them. So that is the classification for the R group because the foundation, remember that C with the NH3 and the CO on the other side, that is unchanged. In other words, this guy. So when we have this, and this, and this, these are unchanged no matter which amino acid you have. So amino acids can be abbreviated either with 1 or 3-letter combinations. So if this is alanine, which it is, and I can tell that by the R group that's up here, this can be abbreviated as a 3-letter abbreviation of ALA, or it can be abbreviated as A. How do you find that? Look for those charts that I'm talking about. This would be a nonpolar R group. Why? Because CH3 is simply nonpolar. So let's talk a little bit more about that. The PI, or the isoelectric point. Okay. So that for alanine is about 6.0. So at about pH 6 or 7 or so, what we find is that this N over here has a positive charge, and this COO over here has a negative charge. As you get into something that is more basic, or a situation that's more basic, now remember, when you go into a basic situation, you're adding what would be like an OH minus. So if you're adding an OH minus, this is like adding a base and getting to a higher pH. Well, this guy is a base, and he wants to go over here and grab a hold of one of those hydrogen. And when he does that, that means that this nitrogen over here loses one of those hydrogen. And so in a higher pH, this would be like more basic situation. Bases are negative. You're going to have a negatively charged amino acid. Now this might be a little part of the video that you need to repeat several times, because a lot of people have a hard time sort of grasping these charges and where they come from and all that good stuff at first. And that is okay. So I want you to know that. On the other hand, as we go into a pH that's less than 6.0, or underneath where the isoelectric point is, we're going to go into a much more acidic environment. And when we do that, we're adding H+, because remember, that's what an acid is. And so as we add H+, we say, hey, this negative charge over here wants to come and grab hold of that H+. And that's where this hydrogen comes from right here. So it makes sense as we go into an acidic media that we end up with a positive charge on our molecule, because it's in a positively charged medium. If you need to go back and repeat that, that is okay. I would certainly encourage you to do that. Thank you, and I'll see you on the next video.